Okay, so the first lecture I talked about the formation of primordial black holes. This second lecture I'm going to talk about observational constraints on their abundance. So as you sort of probably hopefully got the message in the first lecture, personally I don't think that primordial black holes, as either the dark matter or the LIGO events or any other astrophysical phenomena, are particularly well motivated. The difficulty being that it seems to be difficult to make an interesting number of primordial black holes. Maybe there's some mechanism that some people haven't realised yet, but with the physics as we know it, you seem to have to do fine-tuned or unusual things to make an interesting number of black holes. However, physics is an experimental subject, and so at the end of the day, reality is doing what it's doing, and we need to understand it. So the question is, what do observations tell us about the abundance of black holes? So there are a long list of different constraints. I'm afraid this is going to be a bit of a monotonous lecture with just a long list of different things that we go through one by one. I'm going to start off by focusing on the constraints that hold in the solar mass or multi-solar mass region, because this is the area that there's been a lot of interest in recently because of the LIGO events. And initially all of the constraints I'm going to be showing you have been calculated assuming a delta function, mass function for the primordial black holes, i.e. that they all have the same mass. As I sort of said at the end of the last lecture, that's probably not a good assumption, and right at the end I'll come back to applying these constraints to more realistic extended mass functions. But as far as the experimentalists and observers go, assuming this is an opening gambit is a perfectly reasonable thing to do. So first up, I'll start with microlensing constraints. So microlensing is a form of gravitational lensing where the separation of the images is of order microarc seconds, hence the name. And what that means is the images aren't resolvable. So microlensing typically happens when a compact object passes along a line of sight between us and a background object. And in this case, where it's a background star, and so we don't see multiple images, they're too close together to be resolved. So instead what you have is a star, its brightness suddenly peaks and then goes down again. And the key thing here is this brightening should be achromatic, the same in all wavelengths, and it should also be a one-off phenomena if it's due to lensing rather than variability of the star. So going back 20 years or so, there was lots of activity in this area, in particular the Eros and Macho collaborations were monitoring millions of stars in the large and small Magellanic Clouds for many, many years, looking for microlensing events. I've shown here the final Eros collaboration constraints on the fraction in compact objects. So this is compact objects of any form as a function of the mass relative to the solar mass. So we've got one solar mass here, and then some planetary masses down here. And here we've got the Eros exclusion limit that anything above this line is ruled out. So planetary mass compact objects are very tightly constrained, and then the constraints rapidly become weaker once you get above the solar mass region. I probably shouldn't go too much into the backstory here because it's not completely relevant. Macho originally were finding a halo fraction of about 0.5 in roughly solar mass compact objects, but what they found over the years was actually what they were doing was discovering weird and wacky new variable stars that nobody knew existed. So they'd see something that was constant, it would brighten temporarily, stay constant, and then years later vary again. So over time, the Macho results changed, and so in this plot here, they've got their best fit halo fraction here of 0.2 and a sort of loud contour. However, they also did a sort of exclusion limit plot, sort of from the point of view of excluding compact objects, and came up with a very similar exclusion limit to Eros in the range for masses greater than 3 solar masses. So bottom line, microlensing gives you very tight constraints on planetary mass compact objects, which then become weaker once you get into this multi-solar mass region. So these are very long-standing constraints. The LIGO results and the possibility that those binaries could be primordial black hole binaries led people to look at other mechanisms for constraining compact objects in this mass region. And so there was work by Brandt looking at heating of star clusters and ultra-faint dwarf galaxies. And so the idea here being that if you've got a population of fairly massive black holes in some object, gravitational interactions between those black holes or compact objects and the stars is going to heat the stars and cause them to expand. And so he looked at two things: star clusters within dwarf galaxies, in particular a star cluster which happens to be sat close to the centre of a dwarf galaxy called Eridanus 2. And then he also looked at the heating of ultra-faint dwarf galaxies themselves. So these are very small, very dim dwarf galaxies. And so his exclusion limits these lines in red and black here. So again, anything above them is excluded. So these constraints are very tight for very massive compact objects. If you had all of your dark matter in the form of thousands of mass black holes, they would basically wreak havoc, and that's very tightly constrained. But the constraints get weaker again when you come down into this tens of solar mass region, and then you've got different curves here according to whether he's looking at the star cluster or the ultra-faint dwarfs. And then also to do this, you're looking at the present properties of those ultra-faint dwarfs, and it depends on what you assume initially. So there are some significant uncertainties here in quite how tight these constraints are in this sort of interesting region here. Similar sort of follow-up, we had Kushiapas and Loeb looking at mass segregation in dwarf galaxies. And so what's happening here is basically the energies trying to equalize. So if you have very heavy black holes, they end up concentrated in the center of the dwarf galaxy, whereas the stars end up getting concentrated further out. This plot on the left is a fairly extreme case of what would happen. So you get a sort of ring of stars giving a sort of peak in the brightness. That's not what you see when you look at the projected brightness of actual dwarf galaxies. So their constraints here are on the right. So we've got log of the fraction in dark matter. So this is f equals 1, 0.1, and so on, as a function of the mass, going from 1, 10 to 100 solar masses. And they've presented their constraints in terms of p-values. So sort of their constraints effectively somewhere here. And so for comparison, you've got the microlensing constraints here. For some reason, they think Eros and Macho are different, but they shouldn't be. They should be roughly the same. And these lines here are these, for instance, this Eridanus 2 dwarf galaxy constraint that I just showed you. So this is sort of another constraint that applies in that area with roughly the same strength.
I have a question in the previous slide. So what's the mass scale of that ultra-faint dwarf, and also the first one, the star cluster?
The size of the star cluster?
Yes, like how many stars?
I must admit, off the top of my head, I can't remember.
Because I wonder, like, are we able to know the kinematics of the star in ultra-faint dwarf? Because I would imagine that those galaxies are extremely faint.
So your worry is a handful of stars and the velocity. So yeah, one of the things that goes into these calculations is assumptions about the properties of the ultra-faint dwarfs, and hence why you're getting up with these significant uncertainties.
But still, how do we know the size of the baryon part of the dwarf galaxy? Let's say we only, that galaxy has only, like, the stellar mass is only 10,000 solar mass.
And you see there'd be a dozen stars or something observed this year.
We might only see like 10 stars in that ultra-faint dwarf. Then how we know the size of that galaxy, like, and how the gravitational interaction can heat up the.
So I think you're absolutely right in that there are significant astrophysical uncertainties here based on what you assume. So it's a while since I've looked at this paper, so I can't remember a lot of the details. The two black lines, the dot dashed and the solid line, so I think RH0 is the half-light radius initially, and there are sort of assumptions that it takes the value it's observed to have today, but obviously you're right, that's something which would then have big uncertainties, or that it's 2 parsecs. So I think you're absolutely right that there are significant astrophysical uncertainties that come into these constraints. So I mean, all of these constraints I'm going to be talking about, there are astrophysical uncertainties, and for one of them, the one I've actually worked on, I will mention those explicitly. And it would be good to have some really robust constraints in this region. So yeah, it's a good point you're making. So yeah, that was mass segregation. So next up, wide binary disruption. So you do observe in the Milky Way halo binary stars that are really quite far apart. And if there were compact objects in the Milky Way halo, they would perturb these binary stars. Either close encounters would just split the binary up completely, or the cumulative effects of lots of encounters would make the binaries wider and change the distribution of the orbits. So this is something that there's been a sort of sequence of papers going back to Chanamay and Gould, and most recently Monroy, Rodriguez and Allen. So again, here are the constraints for the most recent papers. And so there's a fairly tight constraint which holds for very massive objects, and then that constraint gets very weak, somewhere in the region of tens of solar masses for your compact objects. And there are different constraints here where we're looking at different subsets of binaries. In particular, they tried to pick out the binaries which spent most of their orbits in the halo of the Milky Way and the minimum amount of time in the disk. Because once you go through the disk, we know there are lots of stars there, and they're going to affect wide binaries. So in principle, to me, and I'm not really a proper astrophysicist, but this feels like it could potentially be a really robust constraint. However, the calculations that have been done to date possibly aren't. You need to make assumptions about how the binaries are initially distributed, as in what the size of their separations are, and then be careful about which subsets of binaries you use. So with a collaborator who does know a lot about binary stars and a PhD student at the moment, we're trying to have another look at these constraints to see if we can really firm them up. So we've talked about microlensing and dynamical effects. Now coming on to something a bit different. So you would actually get radiation accreted onto the black holes, which then leads to emission. So potentially X-rays, which could distort the spectrum of the cosmic microwave background, and the spectrum of the CMB is something that's measured accurately with FIRAS, and could also affect the anisotropies as measured by WMAP and Planck. So here, the difficulty is that you're modelling some really quite complex astrophysical processes, in particular the accretion onto the black hole. So there are significant assumptions, and so this is some of the most recent work from Ali Hamoud and Kamil Jankowski, and here are their two constraints depending on exactly how things happen, and the idea is that the reality lies somewhere in between those two lines. And so again, here we're comparing with the wide binaries and the ultra-faint dwarfs. So these constraints, again, at very large compact object masses are very tight and then get weaker into this multi-tens of solar mass region. This dashed line here is the original constraint that was calculated by Ricotti et al., and there are some issues with that, and so the actual constraint is going to be somewhat weaker than this initially very strong constraint, which would have basically killed off this multi-solar mass region for good. Yeah.
Are you saying these distortions are coming from like foreground primordial black holes, or are these primordial black holes that are around at the time the CMB formed?
So this is foreground. This is relatively late. Yeah, thanks for that clarification. This is relatively late times, and black holes then messing with the CMB as it was already produced. Along similar lines, the accretion onto the black holes could also lead to X-ray and radio emission. And so these constraints, I think what my memory serves me correctly, this is basically looking for anomalous point sources of X-ray and radio emission, and you don't see them. So here again, we've got constraints on the dark matter fraction in black holes going from 1, 0.1, 0.02, and then going from 10 to 100 solar masses, with the radio constraints in red and the X-ray constraints in blue. There are other lensing constraints, and this one is actually slightly frustrating. So compact objects around the solar mass could microlens quasars, and so the idea here is that you've got multiply lensed quasars, so you get different quasars with multiple images that are resolvable. And what the microlensing does is affects the brightness of the individual images. And there's been some work historically and also recently by Media Villa et al. Where they've looked at this. And the result is that in this mass range, 0.05 to 0.45 solar masses, only 20 plus or minus 5% of the mass in galaxies, in halos in general, can be in compact objects. So this isn't a detection of dark matter in the form of compact objects. This fraction is pretty much what you expect to be there in stars. This phenomena turns out to be mass independent, so it's actually sort of excluding there being lots of compact objects going more massive than this. The really frustrating thing, for me at least, is they haven't actually published a constraint on the halo fraction in dark compact objects. This potentially looks really constraining, but exactly how constraining it is hasn't been worked out. Similar sort of physics, you can also microlens supernovae, although what's going on here is slightly different. What's affected is the lensing magnification distribution of, in particular, type 1a supernovae. So here, the green line is what you'd expect for the magnifications of the supernovae, how they're spread if the dark matter is something that's smoothly distributed, i.e. particle dark matter. And the dashed line is for a large fraction of compact dark matter. And so what you find is that most lines of sight end up being demagnified, because essentially there's a lower density of dark matter you're passing through because it's clumpy. But because it's clumpy, you also then get this tail going out to higher magnifications. And so there was a fairly recent paper by, however, this is Zubal, Karegi and Selyak, and what they presented were constraints that aren't horribly tight. This is of order a halo fraction of 0.4, but nonetheless the sort of key thing here is that it's applying across a wide range of masses, from 10 to the minus 2 up to multiple hundreds of solar masses. Yeah.
So which cosmological parameters would this be degenerate? Or would it be degenerate?
So the question is, how is this degenerate with cosmological parameters? And I don't know the answer off the top of my head, but there has been this follow-up paper arguing a degeneracy with cosmological parameters. So, taken at face value, this is sort of restricting primordial black holes or any other compact object to be a subdominant component of the dark matter in this region. So, taken at face value, this looks pretty sort of tight. These guys have then sort of argued there are various issues, but the details I can't remember off the top of my head. This is one where I'm waiting for the experts in this area to chip in with an opinion. The third author on this paper is somebody who knows about supernovae lensing. The first two are people who are very keen on primordial black holes, just to put some context on that. So this is another one where it looks like there are some pretty tight constraints, and yeah, we'll just have to wait and see how this pans out. So here is a compilation I made, I think, back at the end of last summer of the constraints in the solar mass region. So this is F on a linear scale between 0 and 1. Log scale of masses between 0.1 solar masses and 100. So we've got the Eros and macho microlensing constraints very tight down here, becoming weaker. And then this bunch of other constraints I've just told you about, which rule things very tight up at 100 solar masses and then get weaker down here. I'm missing on here the microlensing of quasars simply because they haven't published a constraint on F. I'm also missing the supernovae, largely because it was just published after I made this plot. As we've sort of talked about a bit already, there are sort of astrophysical assumptions and modelling which go into these various constraints. So any one of them, it's not clear how robust it might be. But I think what you can take away is certainly 100 solar masses, compact objects are very tightly constrained. The constraints get weaker, but it certainly seems to be difficult for a delta function, mass function, which is what is being assumed for these constraints at the moment, to have all of the dark matter in tens of solar mass compact objects, because there are these various astrophysical processes, the dynamics of dwarf galaxies, the disruption of wide binaries, and also these accretion constraints that then get you into trouble. So before I go on to constraints in other mass regions, any questions? Yeah.
So how much would this change if you relax this delta function assumption?
So the question is, how much does this change if you release the delta function, mass function assumption? That's a good question, and I'll talk about that at the end. Anything else? No. Okay, well then come on to constraints in other mass regions, because even if the multisolar mass region seems to be tightly constrained for being a dark matter candidate, there's a much wider range of possibilities. So microlensing again, nearby stars have been observed by Kepler for sort of planet finding, and because they're very nearby, only about a kiloparsec away, the microlensing gets a bit more complicated, and the source stars, rather than being point objects, have finite size. And what that turns out to mean is that you're sensitive to lensing by much lighter compact objects. So these are constraints by Grease et al. So we've got the log of the halo fraction here is 1, going down to 10 to the minus 2. Their results are here, so they're ruling out all of the dark matter being compact objects with around 10 to the minus 8 solar masses, assuming a delta function mass function. And for comparison, these are the macho collaborations, really quite tight constraints on planetary mass objects. Down here are some results from gamma ray burst femtolensing, which I'll come back onto in a moment. And then this is their prediction for what future observations, for instance with W first, could have done. More microlensing, this time from just over a year ago from M31, Andromeda, our nearest neighbour. Exactly the same principle as the Milky Way microlensing, but what this survey has done is looked at things with a much higher cadence, as in the observations are closer together, which means they're sensitive to short duration microlensing events, which means they're sensitive to lighter compact objects. And so in this case, it gets a bit more complicated because the source stars are individually unresolved, but nonetheless, they've sorted out the issues regarding that. And here is their constraint here on a plot which contains a wide range of various masses. So here we're down to so roughly 10 to the minus 10 solar masses. And it looks like a very tight constraint because they only in fact see maybe one microlensing candidate. However, there's been some subsequent work pointing out that with this below 10 to the minus 10 solar masses, you get the wavelength of light being comparable to the Schwarzschild radius of the black holes, and so you're going to get complications of diffraction and all showing up. So below here, the calculation that's been done to date probably isn't completely valid, and arguments are that these constraints would become significantly weaker down here. Yeah.
On the neutron star issue, I don't really think that's a constraint so much of it. It's a danger zone where the black holes will be.
So you're talking about
the neutron stars? Yes.
I will come on to that in a second, but I'd be very interested to hear, what you think about that when we get there. So more on the lensing. You can also femtolens gamma ray bursts, and what's going on here is you're getting into this complicated region where the wavelength of the light is comparable to the Schwarzschild radius of the compact object, and you get energy-dependent magnification, which would end up producing interference fringes in your energy spectrum. So there are constraints, the most recently from Banaka et al. Using the Fermi gamma ray burst monitor. So we've got constraints down to about 0.1 of the dark matter density, down at around 10 to the 18 grams. So we're getting to the light end of the, sort of the black holes, which are just a bit too massive to have evaporated by the present day. We then come on to some more controversial things, and this is the effects of light primordial black holes on stars. And in particular, primordial black holes would potentially get captured by neutron stars and potentially destroy them. And so the constraint here comes from looking at areas where there are neutron stars observed, where you expect the dark matter density to be high. And so in particular, people have looked at constraints from globular clusters and also to the centre of the LMC and the Milky Way. So we have constraints again here on the fraction of the dark matter in primordial black holes, 1 at the top, 10 to the minus 5 down here. This plot, 1 at the top, 10 to the minus 7 down here. So these are for different regions. Here we've got a dark matter density of 1 GeV per cubic centimetre and a dispersion of 30 kilometres a second. So for reference, the solar radius, the canonical value is 0.3. And then the bottom panels for somewhere with a very high dark matter density, 10 to the 4 GeV per cubic centimetre. So it would be interesting to have some input from somebody who knows more about this area. My queries here are, do we expect globular clusters to contain dark matter? And then there's also been work, more subsequent work claiming about that there was an error in this calculation, but it's one of those areas that it's very difficult for somebody outside to judge the validity of what's going on. But it would be interesting to hear your opinion on this.
Well, I mean, Alex Kosenko and Vladimir Pekistov here at UCLA and I looked at these constraints based on the Tinnikov work, which just looks at how nuclear matter, a neutron star, can just by DEDX essentially trap primordial black holes. So, and this is the mass range that is of order 10 to the minus 10 solar masses, something like that. So it's actually fairly benign. I mean, the statistics that we have on neutron stars are consistent with some destruction of these guys. And so I think...
So potentially it happens, but...
Yeah, in fact, there are even some good things that can come out of it.
Of the R process.
For example.
Okay, but I guess, so you would argue
So
though...
I wouldn't write it as necessarily a constraint, but just...
A probe.
Just an interesting region to look at that may contain a constraint at some point, but right now, what we know is fairly consistent with...
Okay, thanks. And I guess on a probably fairly similar note, people have looked at the effects of primordial black holes on white dwarfs, and the argument here is that as the primordial black hole goes through a white dwarf, dynamical friction would heat the white dwarf, potentially causing it to explode. So here are constraints on the density as a function of the black hole mass. This is the dark matter density in the solar neighbourhood, and so the constraint's dipping below it at about 10 to the 19 grams. Back onto slightly more solid territory, we know that primordial black holes evaporate via Hawking radiation. There's this critical mass of order 10 to the 15 grams, probably actually more like 5 times 10 to the 14, which is the mass of black holes that are evaporating today. Lighter things will have already gone. Slightly heavier things, they will have started evaporating and will be producing gamma rays. And so the gamma rays that you produce can't exceed the measured intensity of the gamma ray background, for instance, by Egret and Fermi. And so here's a constraint which is very, very tight in terms of the mass. There's some uncertainty in how it depends on mass, which depends on the uncertainty in the measured energy spectrum. And so I've just clipped out a bit of a plot here. We've got, I think, 10 to the 15 grams here, halo fraction of 10 to the minus 7 there. So it's a very tight constraint on these black holes that are just starting to evaporate. And potentially even tighter constraints could be placed by subtracting off known contributions to the gamma ray background. There are sort of astrophysical objects like blazars that we know are there and pumping out gamma rays. So if you could model those and subtract them off, this constraint will get tighter. I think nobody's actually really bothered to do that because it's already pretty damn tight. So that was going down to very light black holes. Let's go in the opposite direction up to very heavy ones. So more lensing, in this case it's milli-lensing of radio sources, and in this case the separation of the images is milliarc seconds and can potentially be resolved using very long baseline interferometry. And so here we've got a constraint coming down to about 0.01 of the total density, but out at really high masses, 10 to the 6, 10 to the 7, 10 to the 8 solar masses. There are various other constraints, but because it probably gets a bit boring going through a long list of constraints, I'll just sort of mention them in passing. I think there are various reasons why we can't have the dark matter being 10 to the 5, 10 to the 6 solar mass black holes. Objects that heavy in the halo would just wreak havoc. For instance, dynamical friction would pull them into the centre of the Milky Way, so you'd end up with a larger dark matter density there. They'd also, crucially, heat the disk of stars in the Milky Way and puff that up. And also, because you then actually have a small number density of dark matter, you then get large Poisson fluctuations in the distribution, which would then be measurable in large-scale structures. So I think these are lots of good reasons to rule out extremely massive black holes being the dark matter. There are also some indirect constraints. So these are constraints where you don't constrain the density of the black holes directly. Instead, you constrain the large density perturbations, which are the sort of most popular mechanism for forming them. So this first one is a slightly subtle one, that if you have large density perturbations, you then end up sort of via second order effects producing large tensor perturbations, i.e. gravitational waves, and limits on stochastic gravitational wave backgrounds then end up constraining large density perturbations and hence the production of black holes. That one is one of those constraints that ends up being rather model dependent. It's not a general thing that can be put on a plot, but if you've got an inflation model that you think produces interesting numbers of primordial black holes, you probably need to just worry about this. Similarly, also, large density perturbations on some scales at least could generate spectral distortions in the CMB. And again, this is something that applies to very massive black holes. And then finally, we're looking forward to the future, what different constraints might be coming. Fast radio bursts, strong lensing of those could be potentially detected in the future, and this would be another constraint in this tens to hundreds of solar mass region. And similarly, for quite a wide range of masses, pulsar timing using the SKA, the square kilometre array, could also in the future put tighter constraints on this region. So, yeah, caveats. All of these constraints are put on plots as lines. However, as somebody has already questioned, various assumptions go into the constraints. So, one that I've looked at because I worked on microlensing many, many years ago, so it meant I could just dig out my old codes, update them, and have a look at this without too much effort. So I looked at how the constraints depend on what you assume for the distribution of the dark matter, its density and velocity distribution. So the microlensing, remember, is when we've got a compact object crossing the line of sight between us and in this case, the stars and the LMC and SMC. So what matters here is the velocity with which the compact objects cross the line of sight and also the density along that line of sight. So to do this, I looked at what were called Evans power law halo models. They're somewhat out of date, but they have analytic expressions for the density and velocity distribution, which are what you need to do this calculation. So to sort of demonstrate that the models that I looked at are roughly reasonable, here's a plot of what's called the rotation curve of the Milky Way, the circular speed as a function of radius. And the standard halo model that people tend to assume for these calculations, where you've got a Maxwellian isotropic velocity distribution, rises sharply in the middle and then is roughly constant. The actual data at large radii have a lot of scatter, which is confined roughly within this envelope here. And the two power law halo models I looked at, one has a relatively massive halo with a rising rotation curve, and one has a sort of much lighter halo. So I'm not claiming that either of those models are a good approximation to the Milky Way. What I'm trying to do here is look at models that span the uncertainties in observations of rotation curves. And when I did this, this is what I then found for the constraints on the halo fraction from microlensing. So the standard constraint we've seen many times already from Eros is this black line here. If I stick with the standard halo model and just vary the circular speed, i.e. vary the velocity dispersion of the dark matter, we get a little bit of uncertainty coming in these green curves here, but that's not a huge effect. If you change the local density, i.e. the amount of dark matter here at the solar radius, and vary in this regime here in solar masses per cubic parsec. So for reference, the standard value is 0.008 in these astrophysical units. You end up with a variation between the blue dotted lines here and here. And then for these power law models, you end up with the red dashed line. So you're getting some significant variation in the constraints just by looking at a range of plausible models. And so for some reference, I've put in the dwarf galaxy constraints, the various different ones in pink here. However, my bottom line was that actually it was, if you were wanting the dark matter to be in solar mass compact objects, what you might want to do is move the constraints so you create a gap between them, but actually considering these astrophysical uncertainties doesn't do that. There's still overlap between the constraints that are coming from high masses and the microlensing constraints. It's been pointed out by Garcia, Belido and Kless that clustering of the primordial black holes would affect these microlensing constraints, because if the black holes were clustered, you can then imagine that if you've got a cluster of black holes coming across the line of sight, you get a huge number of microlensing events, but on average there wouldn't be a cluster crossing the line of sight, so it would decrease the constraints. This is a valid point, and as I sort of emphasised at the end of the last lecture, clustering of primordial black holes is something that probably happens and hasn't actually been reliably calculated yet. So it's another caveat to bear in mind, that we're assuming with these constraints that the dark matter in the form of compact objects would be smoothly distributed, but in fact we possibly expect the black holes formed during radiation domination to be clustered, and this would affect things. How it would affect things, we don't know, because nobody's done a completely reliable calculation yet. So, before I come on to extended mass functions, any questions on the constraints so far? Yeah.
I have a question on extra-relative memory breakdown.
That one.
So I was a bit surprised to hear this because...
Sorry, I can't hear you.
I was a bit surprised to hear this because the gamma ray, the black holes, Hawking radiation of black holes are very faint. So for example, like for a solar mass black hole, the temperature is about 10 to the minus 8 Kelvin. So I was just wondering what energy range is, relevant for this?
I've got a vague memory. So the question is the questioner is surprised by these constraints given that individual black holes are very faint, and what energy range is this happening from? I've got a very vague memory of 100 MeV, but the key thing here is that we're not looking for the contributions of individual black holes. If these things were making up all of the dark matter, their number density would be very high, and so cumulatively, even though each individual one would have a small contribution, cumulatively you could potentially get a large contribution. Have a look at those papers rather than trusting my vague memory. Any other questions? Okay, so all of these constraints to date have been calculated assuming a delta function, mass function, because that's a simple thing to do. As I explained in the first lecture, we don't expect primordial black holes to have a delta function, mass function. Critical collapse leads to a range of masses, even if you've got a very sharp spike in the power spectrum so that all of the black holes form at the same time. Also, when people insert features in the power spectrum, they seem to have finite width. So it looks like what you actually produce is something more like a log normal mass function. So what happens when you try and apply these constraints to realistic extended mass functions? The first thing is you've got to be a bit careful. Historically, what people did was just to take the constraints on the halo fraction, i.e. omega in black holes versus omega dark matter, here they are in red, and just plot dFdm for their particular model over the top and go, way hey, doesn't go through any of the constraints, we're all fine. It just doesn't make sense to do this. You're comparing two completely different quantities, f and its derivative. And really what you're doing here is sort of double counting. So for a sort of concrete example of this, let's come back to the Eros microlensing constraint and think about really what this constraint is telling us. And what it is it's for each individual value of mass, it's a limit on the value of f you can have all in that mass. So for instance, here we've got a constraint of about 0.2 for 5 solar masses and about 0.4 for 10 solar masses. So you can have either of those things, but you can't have both of those things. If you had both of those things, you would be violating the observational constraint. So this sort of naive comparison, you're ending up violating the constraints because you're double counting. So you've got to be a bit careful. So the first paper to sort of look into extended mass functions a couple of years ago was by Carr, Kuhnel and Sandstadt. And what they did doesn't work for reasons that are quite subtle, so it's probably worth having a think about why it doesn't work. So here they're comparing Eros and the dwarf heating, and their idea being if you put an extended mass function in here, can you have all of the dark matter being black holes and still satisfy these constraints, which together rule out any delta function mass function. So what they did was they divided the region of interest up into bins, and then they first checked that the mass function integrated across this first bin gave you a halo fraction that was less than the weakest constraint here. They then did bins 1 and 2, 1 through 3, and so on and so forth. The problem is, by comparing with the weakest limit in any bin, you're underestimating the strength of the constraints. If your integrated mass function exceeds this weakest limit, it's very definitely ruled out. If it doesn't exceed the lowest value, it's very definitely allowed, but anything that falls in this gap may or may not be allowed. So the problem was that their way of doing this was underestimating the strength of the constraints. So they managed to find extended mass functions which they thought were compatible with both constraints, but in fact weren't. So, I mean, I initially showed this by actually looking at some concrete examples. So, as I mentioned in the first lecture, it turns out that these inflation models with features in the potential, the mass functions they produce are well approximated by a log normal distribution centered at some mass MC, which depends on where the feature in your power spectrum is, with some width sigma, which depends on how wide the feature is. I sort of spotted this phenomenologically. There was then a follow-up paper that sort of proved it more formally. And so I then had a look at the constraints, Eros microlensing and the heating of ultrafaint dwarfs, because these were the two that could easily be recalculated for an extended mass function. And so Eros microlensing rules out the red region of parameter space, so light masses and narrow mass functions. The heating of the ultrafaint dwarfs rules out the blue region, i.e. heavier masses and wider mass functions. So down here, we're recovering the delta function results, i.e. the constraints overlap, and there's nothing you can do to meet both of them. And actually what you're seeing is once you start allowing broader mass functions, things get worse rather than better. It actually, more of the parameter space gets ruled out, and you making your mass function wider actually makes it harder to satisfy the constraints. So again, this is something sort of I noticed phenomenologically. It's now actually been proved to be a general result. And what people have also done is come up with a general method for any constraint, even if it's something that's really difficult to calculate, so you can't recalculate it for your favourite mass function. Here's a method for applying the constraints that have been calculated assuming a delta function. So this comes from the observation that in general, primordial black holes of a particular mass contribute independently to a given constraint. They don't sort of interact, they just have whatever effect they have, and you sort of add them up. So say there's some observable, A, and you're interested in the mass function here, psi, so that's essentially df/dm. And so generically you can write any observable as some constant plus an integral over the mass function of the product with some function k1, and k1 is dependent on the particular constraint you're interested in. It's some function of mass that includes the underlying physics plus any other astrophysical parameters. And for instance, for the microlensing, you can write down a quite complicated analytic function. A few lines of maths though, and what you can do is write derive the following condition, that the integral over mass of your mass function divided by the maximum constraint for a delta function as a function of mass has to be less than or equal to 1. So what you do is you take whatever the observational constraint for the delta function is. The plots I've shown you, that's what they're showing f max as a function of m. And then you, for whatever mass function you're interested in, you find when this criteria is valid. So this was originally demonstrated by these guys. There was some follow-up work by these guys who then sort of extended the concept to say that every extended mass function is equivalent to a delta function with a particular equivalent mass. The bottom line is the results, and this is that the constraints, once you take into account realistic extended mass functions, are actually tighter than for a delta function. So these are, the general conclusion was reached by Carr et al. Here are their plots. So on the left, we've got the log of the halo fraction as a function of the log of the mass. This is from monochromatic mass functions, i.e. a delta function. So we've got all of the particular constraints I've told you about, and in black they've sort of calculated their envelope, and then here they've recalculated things using the prescription I told you about here. Here they've done it for a log normal mass function for a particular width. You can do it for whatever mass function you like. And so what you see is that the constraints just get tighter. And so here, where maybe if you decided that you didn't like the white dwarf constraint, here you could have just about allowed a delta function, mass function at around 10 to the 18, grams. Once you have an extended mass function, the constraints really get tighter, down to about 0.1 of the halo of the total halo density. You might wonder, though, should you be taking all of these constraints seriously, since some of them we've talked about there being lots of astrophysical assumptions, and in particular the constraints down here from neutron stars and white dwarfs. So there's been some work by a group of people, including Stefano Profumo, looking at the best you can do, as in if you can contrive any mass function you like with multiple peaks, what's the maximum fraction of dark matter you can have in the form of primordial black holes. And so they divided the constraints up into various subsets. On the left, we've got their results for what they call the robust constraints, the ones that it's really hard to see how they don't have to be valid. So, and then here, all constraints. So for instance, the white dwarf and neutron star constraints are in this plot, but not the one on the left. And they've also, in this one, they've got the supernovae microlensing constraints, but not in this one on the right. So they've shown that the best case scenario for satisfying all of the constraints is to have a mass function which is a sum of delta functions with different masses. So this is something that theoretically no one has any idea how you produce it, but they're sort of asking the in-principle question, can you satisfy all of the constraints? And in this case, with some big delta functions down here at very light masses designed to fit in the gaps between the constraints, and some smaller delta functions out here, you could actually quite happily have twice the expected amount of dark matter in your black holes. However, if you start adding in all of the constraints, your best case scenario is this series of delta functions, and even then, even with something this contrived, you could only have about 40% of the dark matter in black holes. Yeah.
So, I mean, earlier you pointed out that hyper-supreme-can constraint actually is a little bit questionable below.
Indeed, so
masses, because the wavelength of light is longer than the Schwarzschild radius, right? So
exactly, so they're robust constraints. This one here isn't. Yeah, no, you're right. So if there was a region where primordial black holes could be the dark matter, it potentially is in this region here where it's difficult to constrain them because this microlensing constraint could be weaker, and you're then into the physics of stars, which is, so yeah, so maybe this conclusion is too strong.
So your point is actually that these extended mass functions don't help.
They make things worse, yeah.
But this is anti-intuitive, right? It's difficult to because if you have an extended mass function, obviously the fraction that you would have, even for the extension of the applicability of each of those. It's something intuitive. I find it intuitive. Is there a way of understanding how come that actually don't?
So I think you're absolutely right that you think that spreading the mass around.
It's a little bit anti-intuitive that you wouldn't get somehow the possibility because under the extension of each of the particular limits, you would have only a certain fraction which would be much smaller than. So it's anti-intuitive. I haven't followed this, so I don't know. But
I mean, you're right, and I probably should give some more thought to this. All I can remember is that I sat in a conference talk where this was presented, and for the microlensing results, I was immediately suspicious, but I can't explain why I was suspicious of the initial claim that extending the mass function made things better. I think it was just my experience of having played around with extended mass functions many years previously, and you're right that in general it's really not
a bit,
obvious. So, I mean, I guess maybe I should be a bit careful. They are tighter for the specific cases that have been considered. So here I'm showing the KRL results for this log normal mass function that seems to show up from inflation models. They've also have the similar results from a m to the power of minus 5 halves.
Is that from scratch and computed from first principles having the data, or they somehow use this processing?
So they use
Because
this
you can also
prescription.
start with the raw data
So-
that they were using.
So that's the thing that I'd be happier with, and that's exactly.
That would be the actual way of doing it, but of course you need the raw data. To
So
do that. I'm not sure if
the diff-
you just brute force or not. I mean,
You're absolutely right. This is something you want. That's how you'd want to do this, and so that's why I only looked at these two constraints because I could do
because
that.
you could do that. Right?
Exactly. So it would be nice to see some of these other constraints recalculated from scratch to give
from
complete.
first principles and see if they coincide.
Yeah. So I think they do coincide. For at least for the cases I was able to do from scratch.
They do.
Yeah.
They do.
So that gives you some confidence that this is working.
I think the point is, if you go back to the prescription how to do this. Yeah. The thing to look at here is that you actually divide by the mass fraction demand is smaller than 1. So the constraints actually don't get tighter. It's just that you sum up all the primordial black holes that you have, and you must not get basically above 20% of the energy density of the universe. I think this is the point. This is what, at least in my understanding, the counterintuitiveness of this is that constraints don't actually get tighter. It's just you have more stuff in.
What do you mean
Very
by
simple.
stuff?
You have more primordial black holes that can make up your dark matter than just a delta function. I think it's where the counterintuitiveness comes from is the fact that one says the constraints get tighter, but this is misleading. I think, at least in my understanding of the Carr paper, where the two plots come from.
I haven't really thought much about it. Maybe it makes sense that once you integrate, you would, but it's.
So can I question why you think this is misleading? Because in terms of constraints on the halo fraction of F, they do become tighter when going from a monochromatic to a log normal.
Let me follow that with another question. This is on the right hand side is for a very specific mass function, right?
Yeah.
And a very tight one too, right? It's like from 20 to I don't remember. I read this paper whenever it came out. So by misleading, I mean again the semantics of saying that the constraints get tighter. again, I might have a naive understanding of the prescription from the slide before. I think it's a way of reformulating what the constraints show and what the extended mass function does in terms of adding up to all of the dark matter.
Probably best if we talk about this
Yes,
offline.
let's do that.
But so I think you're entirely right that this seems counterintuitive. This is being done on a case-by-case basis. They've also found the same result for a mass function that's a power law. So, and it would seem, so these guys' results would seem to back this up in that the best thing you can do being sums of delta functions. But I agree it's counterintuitive. I'm basically almost finished. It's probably, before we have any more discussion, would be a good time to sort of hit some conclusions. So the main theme of this lecture is that there are actually lots of observational constraints on primordial black holes or other compact objects as dark matter. So for instance, gravitational lensing on all sorts of scales, their dynamical effects on the stars we can see, also accretion and other astrophysical processes. I'm talking here about their effects on neutron stars and white dwarfs. The sort of caveats to bear in mind here is that these constraints involve assumptions about the dark matter distribution and or modelling of complex astrophysical processes. So some of them possibly aren't as robust as you might like, or they have uncertainties. However, it does appear that it's difficult for primordial black holes to make up all of the dark matter, and in particular in this multi-solar mass region that there's been recent interest in. And the other thing to bear in mind is that the constraints seem to be tighter for these realistic extended mass functions that you expect from models of inflation, whereas the calculated constraints that you usually see are calculated assuming a delta function. So, bottom line, it seems like primordial black holes could be some fraction of the dark matter, but at the moment it looks difficult, but possibly not ruled out, for them being all of the dark matter, in particular in this multi-solar mass region. So that's it. Any more questions? We do, I think, have time. Yeah.
So I would like to continue the question on primordial black holes and astrophysical black holes. Is it possible there is a third possibility that there are dark matter particles in early universe and they don't form black holes before the CMB form, and then after the CMB has formed, these dark matter particles form black holes? And I ask this because if I understand the Jeans instability correctly, I think dark matter particles are more easier to form black holes than ordinary matter, because first they have larger mass. Secondly, they have very, very small pressure. Their interaction is very small. There is no radiation pressure, no ordinary matter pressure. So the pressure is so low that they are very easy to collapse into black holes after the CMB era.
So the question is about the difference between astrophysical and primordial black holes as dark matter, and in particular the possibility of black holes forming from matter after the formation of the CMB. Is that correct? There's a brief summary before I attempt to answer.
It's like astrophysical black holes forming of dark matter particles.
Right, so I think what we've got going on here is we need to define some terms so we're talking about the same thing. So certainly what I mean when I say astrophysical black holes is black holes formed from stellar collapse or some other sort of astrophysical mechanism. Whereas I think what you're thinking of here is actually primordial black hole formation during matter domination, as we discussed earlier. So I think what you're thinking about would actually fall into the category of primordial. Relatively late compared to what we were talking about earlier, but still nonetheless early compared to black holes that are formed through stellar collapse.
Okay.
So I think it's a question of terminology.
Okay, I see.
Yeah.
I was wondering if you could speak just in general a little bit about growing black holes. So, just one way to have an extended mass function is if you start with a delta function and then some of them grow. But just from things that I've heard, growing black holes is kind of a very complicated thing, and it's hard to do. I don't know if this is interesting at all.
Right, so the question is how the possibility of growing black holes and whether that happens and how it changes the mass function, and in particular potentially turns a delta function into something broader. This is not something I know a huge amount about, and it's also complicated, but I think the general point that it's something that probably needs to be taken into account is a valid one. So I guess there are various things that could happen. First, you can grow black holes by having them merging, and as I sort of hinted at the end of my first lecture, that's really not a calculation that's been done properly. Were you also thinking about individual black holes growing via accretion?
Yeah.
So my understanding, but it's only a very vague one, is that during radiation domination, that's only a small effect. It doesn't change things much. People have looked at more complicated scenarios. I've got a vague memory of some work by Rachel Bean and João Maguagio where they tried to grow primordial black holes into supermassive ones by having them eat in quintessence. But again, I can't remember much of the details and viability of that. So I think the general point is, yes, this is something that should be taken into account, even just mergers, but it's a difficult calculation to do. I don't know if anyone else wants to add anything to that answer.
I have a question. I want to continue his question. So there was a paper about dark radiation and how the dark matter can be cooled by dark radiation. And so they were saying that the dark matter can dissipate, eventually come into the denser object, and they are entirely made of dark matter. And so maybe in that case, that object would eventually collapse into a black hole. I'm not sure what the time scale of forming into a black hole. But my question is about observation. Let's say we have many dark matter clouds, and they are quite dense, and maybe their mass scale is 10 to the 2 to 10 to the 6 solar mass. Can we use the pulsar timing array technique you just mentioned, the Shapiro time delay, and also the micro-lensing technique to put a constraint on this object?
So the question is whether dense dark matter clumps that aren't black holes but just dense.
Yeah, they can dissipate, yeah.
So you're absolutely right that some of these constraints I've talked about can also be applied to clumps of dark matter. So the specific things that I'm aware of people looking at are these ultra-compact mini halos that I mentioned that could be formed from WIMP dark matter. There are also axion micro halos, 10 to the minus 12 roughly-ish solar mass objects that could be formed. And people have looked at both pulsar timing array constraints and microlensing constraints on those objects. So for the axions and the microlensing, there's a couple of papers by Malcolm Fairbairn and collaborators that do that. So you're absolutely right that some of these phenomena don't just apply to black holes, they apply to more extended but still dense clumps of dark matter.
If that thing can exist, then how do we tell the difference between those objects and the primordial black hole? Does the density profile matters in that case?
So the density profile does affect things, and the calculations people have done, they've had to feed that in. What I don't know is, so you're thinking maybe, for instance, a microlensing event, would the exact profile depend on that? It's a good question, which I don't know the answer to.
Because I guess maybe in Shapiro time delay technique, the mass profile matters. Let's say the photon falls into a black hole, so that's infinitely redshift. But if that thing falls into dark clouds,
then it would be different, yeah.
Out, so they are two different things. So maybe density profile matters. But
I think you're probably right, yeah.
Okay.
I have two questions. So the first question is on the microlensing. What gives the sensitivity shape of the lensing, or why is it more sensitive to the mass on the planar, like a planetary scale than the solar mass scale? And my second question is, when we do the microlensing experiment, you're looking at the brief change in the brightness. So on what time scale does this change in brightness happen? And so for this to work, we need to know how fast the objects are moving in the line of sight. For example, could it be that the compact objects are moving so slow that we are actually looking at a object which doesn't appear to change in brightness, but it's just that the object is moving too slow for us to sense the change in brightness?
So I think that question, I'm assuming, was nicely audible, and there's no need to repeat it. Okay, so the question was about microlensing and how the timescales of the events are related to the mass, and also how assumptions about the velocity of the objects fold in. So yeah, I sort of didn't go into very much detail, but the duration of the event is determined by the mass, and so hence that's actually the reason why the constraints from the HSC constraints from M31 apply to shorter, smaller masses. So what happens is you basically point something with a wide field at a bunch of stars, go away, come back a bit later, do it again, and so the duration of the events you can detect is determined by the cadence of your observations, as in if you're only looking, say, every 10 days, you're not going to see an event with duration 2 days. So I can't remember the details off the top of my head, but the Eros and Macho collaborations had some detection efficiencies, i.e. the probability of seeing an event if it occurs, that were small, less than of order 10 days, peaked at of order hundreds of days, and then declined again. And so it's that efficiency for detecting things that then dictates their sensitivity in terms of masses, i.e. the events that come from very light planetary things they'll definitely see. Once you get up to tens of solar masses, I think those events were then too long to be picked up by the duration of the survey. So does that answer your first question about masses roughly? So then the velocity, you're absolutely right that how long an event lasts is also going to depend on how long it takes the compact object to cross the line of sight. So as I've tried to emphasize, all of these exclusion limits rely on astrophysical assumptions and modelling. So the standard calculations are done for something called the standard halo model, in which the dark matter has a Maxwellian distribution, so roughly Gaussian. The exact shape of the velocity distribution, that's something that there maybe is some uncertainty in, but the typical velocities, I don't think there is a huge uncertainty, because what's sort of coming here is that we can measure the local dark matter density quite well, and that's essentially creating a potential well, and that's what causes the typical velocities. So it would be very difficult to change the typical velocities to make them very small or very large, and hence dramatically change the durations. So you're right that there is some uncertainty in the constraints from uncertainties in exactly what the velocity distribution is, but you can't change it so wildly as to completely change the constraints. Actually, I think you have your hand out before.
First him and then you.
Oh,
Yes.
oh, I just had like a small point about the microlensing thing. So the curve that you see, its amplitude also depends on the geometry of the source and the object.
Yeah.
And the geometry will also determine how fast this transit happens.
As in what angle you're crossing the line of sight. So you integrate over that to get a probabilistic. But yeah, you're right, there's a vast simplification to sort of try and get the principles across.
Yeah, so sort of, I guess, maybe a more naive question about how black holes change over time. But it seems like black holes could either get more massive or less massive via radiation or accretion over time. But we have sort of, we have the CMB, which tells us about the dark matter really early on. And then we have also like very modern day things like galactic rotation curves. So is there any constraint on black holes as dark matter that comes from needing these things to be consistent? Or?
So the question is whether there's any constraint on black holes as dark matter from the fact that we've got good measurements of some dark matter abundance from the CMB, which is in some sense an early time phenomena versus late time stuff. Although actually I think a lot of this, no. So I think for other dark matter candidates, for instance decaying dark matter, you would be right that there are things that go on. For the black holes, I think we expect accretion to be fairly small, and then the evaporation, to a pretty good approximation, just happens as a bang at the end. So hence there are those really tight constraints on black holes that are just starting to evaporate. But for the vast majority of them, the evaporation doesn't change their mass right up until the last bit of their, and that's something that's very well calculable, so isn't a thing.